The Perseverance rover captured this panorama as it was ascending to the rim of Jezero crater during its fifth campaign on Mars. The scene shows just how steep some of the slopes leading to the crater rim can be. The rover made the ascent in order to explore a region of Mars unlike anywhere it has investigated before. Taking about 3.5 months and ascending 1,640 vertical feet, the rover climbed 20% grades, making stops along the way for science observations. Since landing at Jezero in February 2021, Perseverance has completed 4 science campaigns: the crater floor, fan front, upper fan, and margin unit. NASA scientists are calling Perseverance's 5th campaign the Northern Rim because its route covers the northern part of the southwestern section of Jezero's rim. This phase began following a challenging climb up the western rim of Jezero crater, marking a transition from studying floor sediments that partially filled Jezero crater when it was formed by a massive impact about 3.9 billion years ago, to exploring ancient rocks uplifted from deep within Mars that were thrown upward to form the crater rim after impact. Studying these rocks is important because they represent pieces of early Martian crust and are among the oldest rocks found anywhere in the solar system. Investigating them could help scientists understand what Mars and our own planet Earth may have looked like in the beginning. Over the next several years of the Northern Rim campaign, the rover is expected to visit many more sites of geologic interest, take several samples, and drive many miles. A key objective for Perseverance's mission on Mars is astrobiology, including the search for signs of ancient microbial life. The rover will characterize the planet's geology and past climate, pave the way for human exploration of the red planet, and be the first mission to collect and cache Martian rock and regoliths such as broken rock and dust. Subsequent NASA missions, in cooperation with European Space Agency, will then send spacecraft to Mars to collect these sealed samples from the surface and return them to Earth for in-depth analysis. As spring activity starts and the seasonal polar cap begins to sublimate in Mars's northern hemisphere, a layer of dry carbon dioxide ice covers the Martian sand dunes. As sunlight warms the dark sand beneath translucent ice, it turns the bottom layer of ice directly into gas. As gas pressure builds and bursts through the ice sheet, it ejects dark dust and sand in fan-shaped patterns as seen in this observation. At this time in early Martian spring, the fans are visible between the sand dunes. The ground between the dunes is on the scale of tens of centimeters, and ice in places where the sun hits more directly will thin fastest, releasing the jets. Later, the ice over and around the dunes will rupture and more fans will appear on the dunes. These impact craters in the northern middle latitudes on Mars have interesting interiors. All of them have wind-blown, aeolian ripples. Outside of the craters and along the crater floors, the ripples are all oriented in the same direction. However, along the walls of some of the larger craters, the ripples are situated radially away from the center, indicating the winds moving inside the larger craters can be influenced by the topography of the crater wall. Additionally, many of the larger craters have layered mesas along their floors that are likely sedimentary deposits laid down after the craters formed, but prior to the development of the aeolian ripples. This incredible panorama was taken by the Perseverance rover, and it shows the mountains, boulders, and other features atop a delta at Jezero crater. The delta formed billions of years ago from sediment that an ancient river carried to the mouth of the lake that once existed in the crater. The mountains seen in the background are the rim of Jezero crater, and the brown hills visible in the middle distance are part of an ancient delta, where a river hit a lake in the crater. Jezero crater lies exactly on the border between the ancient highland region of Terra Sabia, where rocks from 4.1 to 3.7 billion years ago can still be found, and the 3.9 billion-year-old Acides impact basin. The Nili-Fosse-Graben system, which roughly traces the curved shape of the rim of Acides basin, was formed by the impact event as a result of tectonic fractures. The Acides planitia or plains is made up of much younger deposits and formed in the Martian Middle Ages, some 3.7 to 3 billion years ago, modified up to the present day. To the southwest of Jezero crater is the volcanic region of Sietes Major, where lava flowed around 3.7 to 3 billion years ago. Thus, the rocks and deposits in and around Jezero span the geological history of Mars. Due to the diverse mineralogy at the crater, Perseverance rover is currently studying them directly, as it can be used to infer the environmental conditions at the time of the mineral's formation. A detailed map of Jezero crater has also shown that the crater rim is breached by three valleys that were former rivers. Neretva valleys and Sava valleys were inflow channels that have created two deltas on the western and northwestern rim of the crater, and Perseverance is examining the larger of the two in the west in more detail for now. The Pliva valleys in the east of Jezero used to be an outflow channel through which water was discharged from the crater. As such, Jezero is known as an open basin lake, a type of lake that is thought to have once been numerous on Mars. Compared to closed basins with inflow but no outflow, Open basins are interesting because they hosted freshwater lakes with a stable water level. Lakes in closed basins, on the other hand, were subjected to more frequent periods of drying out, which turned them into salt lakes, thus making them less promising in the search for conditions that are conducive to life. Jezero crater's map shows the water catchment area of the two inflow channels, from which material from the surrounding area was transported by the rivers into the crater and deposited in the two deltas. Spacecrafts orbiting Mars have used spectrometers to detect a variety of minerals in this catchment area, which are mainly silicates from the olivine and pyroxene groups. Both mineral classes originate from magma within the Martian mantle and indicate basaltic volcanic deposits that were not subject to long-term weathering by water. Carbonates identified on the inner rim of the crater, together with the clay minerals, testify to weathering by water of rock with a volcanic source. Volcanic minerals, carbonates and clay minerals are observed both in the delta and elsewhere in the crater, and some carbonates or limestones are thought to have been formed directly in the lake. While such lake carbonates, and especially the clay minerals, indicate freshwater conditions and have the potential to preserve traces of life, other types of minerals, such as sulfates that contain iron oxide, amorphous silicon oxides, and hydroxides, have also been observed. These tend to form in acidic waters that gradually dried up, which therefore indicates that the environmental conditions in Jezero became drier and less conducive to life at a later stage. However, even among these minerals, there are some in which biosignatures can be very well preserved. Studying rocks and minerals with a wide origin, whether formed by volcanic activity, by water, or modified in giant impact events, is very important, as it will provide important insights into the history of Mars. While rover missions provide essential groundwork, even more insights can be gleaned by humans working in high-tech laboratories back on Earth. That is why Perseverance right now is also collecting samples from a range of locations and storing them on the surface of Mars to be retrieved by future missions.